Hi everyone, welcome to Bioorganic Chemistry. In the previous lectures, we have studied what are carbohydrates, how they are classified, and how to interconvert open and cyclic structures of carbohydrates. Today, we are going to look at some of the important properties of carbohydrates, such as anomers, anomeric effect, mutarotation, glycosides, and disaccharides. We have studied how glucose exists in equilibrium between two different cyclic forms and its open chain in solution. If you take glucose, only 0.02% of this exist in open chain form. And this cyclization result into two different isomers as a result of the chiral center created at carbon number 1, which is not chiral because in the open chain form we have sp2 hybridized carbon center, which the newly formed cyclic structure always have a new additional chiral center. In glucose, we have beta D glucose, which is always 64% compared to alpha D glucose. If you look at the cyclic structure here, the most stable cyclohexane-like structure or chair conformation, it is represented in such a way that at carbon number 1, this newly formed chiral center, upon cyclization, what we have hydroxyl group, which is in the axial position. And in the beta form, which is thermodynamically more stable for glucose, the hydroxyl group is at the equatorial position. And glucose can exist also in the form of Furanose ring, that is the 5-membered ring. So, but these possibility of having alpha or beta Furanose are very small percentage. Predominantly, it exists in the Pyranose form. So it means that when you have a glucose solid in solution, if you disperse them, this can exist in 5 different structures. So how the Furanose exists? Furanose also forms a similar structure as we have studied how to convert 5 carbon-containing pentoses such as ribose, which is an important sugar in terms of nucleic acid. We will see as it is one of the important component in ribonucleic acid. So this also exists in alpha and beta form. So alpha D ribopyranose, furanose, and beta D ribofuranose. If you take ketoses, they also form cycle structure, again multiple forms, but mostly you find such as when they are in disaccharides, such as in sucrose, they are in furanose form. It can also form pyranose when the hydroxyl group at the attached to carbon number 6 is in nucleophilically attacking carbon number 2. The difference here is that the anomeric carbon in aldoses is C1, but because the function group in this case is at 2, this is at carbon number 2, the anomeric carbon in ketoses. Now then, what are anomers and what is anomeric effect? So we have studied that if we take glucose, it can coexist in solution in two different forms. Predominantly beta form is 64% and a small amount of other cyclic form, and then about 36% of axial, the alpha form. And this stereochemistry, therefore, we often write that stereochemistry unknown, as there will be a mixture of isomers. And particularly what we see here is this particular carbon, this is hemiacetal, because there is still an hydroxyl group that can be functionalized. You can convert into ether. So this semi-acetal group is very labile, and this leads to rapid interconversion of sugars when you dissolve in water. So what are anomers? Anomers, in this case, I said we are creating a new chiral center when we cyclize open chain form. And because there is a chiral center, the stereochemistry of alpha and beta forms are different at only at carbon number 1. So these are a special case of diastereomers where the stereochemistry of a hydroxyl group is different at carbon number 1. The isomers, they differ only in the stereochemistry at hemiacetal carbon or carbon number 1, and this particular carbon is known as anomeric carbon. So we have anomers, we have anomeric carbon. But as we studied in glucose, always the beta form is much more stable, thermodynamically more stable. However, it is not always true in sugars, and many cyclohexene having heteroatom like this. Here in this case of oxygen, you can replace maybe with some other heteroatom such as sulfur. So in this case, a mannose is very closely related to glucose, except the stereochemistry of at carbon number 2 is slightly different, which it makes the stereochemistry of hydroxyl group here position in the axial position. As you can see, in contrast to glucose, alpha D mannopyranose is much more favorable, whereas beta D mannopyranose is less stable. But in glucose case, it's completely opposite. Why is it so? And this particular effect where axial substituent is much more favored is known as the anomeric effect. And then it is a stereoelectronic phenomena where an electronegative substituent such as OH or alkoxy group or even chlorine or bromine on the anomeric carbon, and the carbon number 1 of a cyclic sugar, which prefers an axial position counter to typical steric hindrance that favors the equatorial position. So if you look further, this is a phenomena often observed in carbohydrate chemistry, first observed in the 1940s by J.T. Edward and Raymond Lemick, and they found that unlike in cyclohexane, the simple cyclohexane ring, where when you have a substituent, it favors equatorial position to avoid 1,3 diaxial interaction. Whereas in carbohydrates, many often the axial isomers with a hydroxyl group or electronegative substituent positioned in the axial or the alpha anomers are much more favorable. Then why this is favorable, we can look into the more into structural aspect of this. Few things we can look. Here is an example of if you take glucose, treated with methanol under acidic condition, you will end up with the two isomers or anomers, the alpha and beta. Now, if you look closely, this oxygen, which is called endocyclic oxygen, that means the oxygen which is within the ring or is a part of a ring. And this oxygen, which is oxygen attached to the electronegative substituent at anomeric carbon, this is called endocyclic, that's outside the ring. Now, there are lone pair of electrons in both this oxygen, endocyclic and exocyclic. When they are in the equatorial position, you see there is a steric repulsion and then also a strong dipole-dipole interaction that also lead to the repulsion. But these are minimized when we have the axial position. Both the steric repulsion is reduced and dipole is also minimized. These are the two reasons. There is one more reason. If you carefully look at, there is this anomeric carbon, carbon 1 and electronegative substituent attached here. There is a sigma star orbital. And when it is in the axial position, the sigma star orbital can slightly overlap because of the orientation at around 180 degree. Whereas in this case, this has limited overlap possibility. So this particular process is called as hyperconjugation. And this hyperconjugation also stabilizes this kind of structure. So anomeric effect is the effect that routinely observed in carbohydrate chemistry, where the axial electronegative substituents are favored unlike the equatorial position. And this is due to repulsive interaction, dipole minimization, and hyperconjugation. So now the next topic for us is mutarotation. Then what is mutarotation and how we can understand this process? If you take glucose, a table sugar, and if you take one of the pure forms, such as alpha D glucose, it has a specific rotation of 112 degree. The specific rotation of beta to glucose is about 18.7 plus 18.7 degree. Now, alpha D glucopyranose has a melting point. If you take the table sugar, if you measure the melting point, about 146 degrees Celsius. If you isolate the pure beta form, you can obtain it by dissolving the sugar and in water and crystallizing it by heating at 98 degrees Celsius. Then you will get another form, that is the beta form. It has melting point of 150 degrees Celsius. Now, beta is always more stable, as we know in case of glucose. Now, when you take pure alpha D glucose, which has optical rotation of 112 degree plus 112 degree, it will change if you add water to plus 52.7 degree. Pure beta D glucose has optical rotation of plus 18.7 degree. If you dissolve it in water, it will also turn into 52.7 degree. What we see here is that both of the pure forms, when they dissolve, ultimately they will give a same value of their optical rotation. And this change in the optical rotation is due to the interconversion of their form. That means when you add them into water, it transforms slightly into open chain that lead to the interconversion from one form to another form until they reach equilibrium. Then you get a stable optical rotation of plus 52.7 degree. This process of change in the optical rotation due to interconversion to anomers between alpha and beta through open chain form is called mutarotation. Muta means change, same as mutation in genetics. Our next topic is glycosides. And what are glycosides and what is glycosidic linkage? So, if we take a sugar such as glucose here, this is an hemiacetal. That means you can still functionalize this hydroxyl group attached to anomeric carbon. The acetal of this, that means if you add one more alcoholic functionalization such as ether linkage here, then it becomes a glycoside. The acetal of any sugar is known as glycoside. That means it is always associated with the anomeric carbon, that's carbon number 1. The bond between the anomeric carbon and the alkoxy oxygen is called the glycosidic linkage. So when we refer glycosidic linkage, therefore we always start or begin with the anomeric carbon. The glycosides of glucose is called glucoside. If the ring is pyranose, then it's called pyranoside. If it's a glucose in a pyranose form, glucopyranoside. Furanoses are known as pyranoside. In this case, if you treat glucose with acid and add it methanol or ethanol, then you will get methyl beta D glucopyranoside and methyl alpha D glucopyranoside. So now we have this linkage here, which is glycosidic linkage. Why in the case of glucose and adding an acid and then methanol forms two forms of structure? Of course, one of them is more stable. That's because when you add acid, this is highly electronegative, so it abstracts a proton. And this will lead to the dehydration and a double bond formation, which is very less stable. Then alcohol has the nucleophilic attack at this anomeric carbon. Now, because this carbon is sp2 center, we expect that there is a two different isomers as you can attack from both sides. So therefore, you end up getting two different glycosides in this case. Now, before we move on to the next, we look at some of the simple reactions of monosaccharides. As we know that carbohydrates are polyhydroxyaldehydes and polyhydroxyketones. That means we expect many of their reactions very similar to aldehydes and ketones. But because these aldehydes and ketones are there under certain conditions, they can also undergo some changes or interconversion. One of the important property is the reducing ability of sugars, particularly aldoses, which can undergo oxidation very easily, and they can oxidize. They can undergo oxidation and reduce some of the materials and chemicals. So there are Therefore, carbohydrates are divided also into reducing and non-reducing sugars. Then what is a reducing sugar? When we say that reducing sugar, they always have a free aldehyde group or ketone group in their open chain form at the anomeric center. So if you write in equilibrium, because this is an hemiacetal, we can still have an anomeric center with a carbonyl group. So therefore, they can donate electron and they can thereby reduce other compounds and themselves undergo oxidation. If you look at here, glucose is a reducing sugar because there is still possibility that this is an hemiacetal. Fructose is a reducing sugar because it is also hemiacetal, as this hydroxyl is still free. In glucose cases, we can simply look at carbon number 1 and say whether it is reducing or non-reducing, and same in fructose at carbon number 2. What are non-reducing sugar? Non-reducing sugars meaning their carbonyl carbon is locked. They cannot open and form open chain form, which prevent them acting as a reducing agent. So sucrose, for example, it's both anomeric carbons are locked. There is no free hemiacetal available. That means it is a non-reducing sugar. So the reducing sugar have hemiacetals, and all acetals or ketals are non-reducing sugar. So we discussed that what are acetals, ketals, and glycosides, and reducing, non-reducing sugar. Now, because they have aldehyde group, they have many other functional groups such as hydroxyl group. If you treat it with the base, they can undergo some rearrangement, or they can isomerize into a different carbohydrate molecule. If you take a glucose, this particular hydrogen at carbon number 2 is highly acidic. If you treat it with a base, it can abstract a proton, and as a result, we can get a double bond in this case. And it can then, when it reacts with the water molecule, then or a base, then it is possible that there are two ways that it can abstract a proton. So this result in another isomer or diastereomer. These are called also known as epimer, because hydroxyl group position is very changing only at carbon number 2. So if you take glucose, simply add base, then it can interconvert into also mannose. Same for mannose. If you add base, it can convert into glucose as also. They can coexist. And this particular process of forming isomers catalyzed by base, where one of the chiral center is inverted, is called epimerization, so which is a diastereomer by itself. So here is a mechanistic insight for this. What actually happens if you have a base, proton is abstracted, and it forms kind of an inolate anion. Then a proton is abstracted from water, which result in inverted stereochemistry, or both possibilities. So that means it exists in equilibrium through an inolate anion. Now it can also undergo another rearrangement. If you have glucose, because it has aldehyde, if you treat it with the base, it abstracts the proton, same as I said, but it can also do slightly a in diol rearrangement. Now we have a enol here in double bond, and we have two hydroxyl group. Now instead of the previously shown epimer formation, it can also excess base can abstract proton from here. This will lead to the rearrangement, which ultimately a glucose can lead to the formation of fructose. So if you have a base, if you want to distinguish glucose and fructose, if you are using a base, it is not possible to distinguish. Both glucose and fructose will give a positive test in the presence of base if you do any kind of chemical test or qualitative analysis. So they can also undergo some reduction reaction. It can lead to both aldehyde and ketones. Aldehyde can undergo reaction to result in alcohols. So very simple is a borohydrate, which is a very rich source of hydrogen. If you treat with the carbonyl compound, what you expect is that you will end up in an alcohol. So if I take glucose here and it has an carbonyl group, we end up having a carbonyl compound. Remember, there are no chiral center generated because still it is CH2. But we can also obtain the same from another molecule, that is fructose, because it's a ketone. But in the fructose case, we have to remember this carbon center is sp2, so that means we may end up an inverted stereochemistry in this position carbon 2 also. That means we can get two types of products. One may be glucitol, other is mannitol. Then mannitol can also be obtained from mannose. So it's very interesting, like if you take glucose or if you take fructose and mannose, you might end up when you reduce them in the same product or similar products. So they can also be oxidized using bromine, but bromine is very specific for aldehydes because of the mechanism how the bromine oxidizes aldehyde into carboxylic acids. So aldoses undergo oxidation in the presence of bromine, which result in what we call aldonic acid or carboxylic acid. The color suddenly can be changed from red to colorless. This is used to distinguish or determine whether a given monosaccharide is aldose or ketoses. Ketones do not undergo oxidation in the presence of bromine. Another interesting test for aldehydes in sugars is Tollens reagents, which is nothing but silver nitrate in the presence of ammonia and base. Now again we are using base. We can remember from our previous explanation that whenever there is a base, aldoses and ketoses can interconvert. They can exist in equilibrium. That means this Tollens reagent test will give positive reaction for both glucose and fructose or aldoses and ketoses. And here it is what actually happens eventually is that silver nitrate is in the +1 form will be reduced to metallic silver, where your carbohydrates, aldoses or ketoses, undergo oxidation to give aldonic acid as the final product. And you can see a beautiful silver mirror, which is a metallic silver if you do this kind of reaction. Now, there are many carbohydrates which are naturally available. And we have seen how we can hypothetically increase the carbon number and the right structure. But there are also important carbohydrates. They are not naturally available. In that case, we need to carry out a synthesis. We can use simple building blocks such as we shown glyceraldehyde or trioses, tetroses, or pentoses, increase the carbon number. And one of the very early experiment was a Kiliani-Fischer synthesis, which involves the nucleophilic addition of cyanide to this carbon center. And this will result in two different isomers. Again, for the same reason we have been discussing throughout, this is a sp2 carbon center where nucleophilic attack can happen from both sides. And once you add, then you can slightly reduce using a Linder catalyst. Linder catalyst is nothing but a special palladium-based catalyst which is deposited on calcium carbonate. It catalyzes the addition of hydrogen across this triple bond. And then you can do an acid treatment. You cleave this imine bond. This will give you an aldehyde. Because we carry out this reaction through nucleophilic addition, you will end up with the two different types of isomers. Now maybe we are interested not only construct higher length, but we also want to degrade because there may be some important tetroses or pentoses which are not naturally available. So we have to we can use naturally abundant hexoses and degrade them. But it can also be a very good degradation test to determine in olden days what is a given carbohydrate, because number of steps takes will also help you to determine. So this one of the simple degradation is called Wohl degradation, where it involves treatment first with ammonium hydroxide. This will result in oxime, and this can be then treated with acetic anhydride, as is shown here structure. That is to protect this hydroxyl group when we do the next reaction. So as a result, you can then further treat it with the base. You will end up having your aldehyde. So we have 1, 2, 3, 4, 5, 6, and at the end we will have only 5 carbons. So if you do one more step, then you have 4. One more step, we have 3. That is glyceraldehyde. Now we have studied monosaccharides throughout and their structure, interconversion, and also how we can understand the properties, anomers, the glycosidic linkage, ether linkage formation, and their stability. Now we can look a bit more about disaccharides. Disaccharides are those sugars which have 2 sugar units linked together through a glycosidic linkage. We have already studied what is a glycosidic linkage. Glycosidic linkage is the linkage at the carbon at anomeric carbon with the oxygen of electronegative substituent. Now if we take 2 sugar molecule at the end, if we link them together, now we have a glycosidic linkage. Then how to name this glycosidic linkage? We can name the carbon number them accordingly. And it's always from this end, from the anomeric carbon end, we start. So this is now the hydroxyl group was in a beta. So this is oriented in the beta position. So it's a beta. And anomeric carbon is at carbon number 1. And it is attached to the carbon number 4 in the other. So we can say this as a beta 1,4 glycosidic linkage. In case if it is 3, we say beta 1,3, 2, we say beta 1,4. What if as an axial hydroxyl group, then we say alpha 1,4, 1,2 or 1,3 linkage. So this takes the predominance. Now again we have studied reducing and non-reducing sugar. If you look at this has 2 ends because this is now an acetal. But this is an amiacetal. Therefore, this is still a reducing sugar. So if we take galactose, for example, it also has a beta 1,4 linkage. It has a galactose and D-glucose linkage. And previous example was xenobiose. And important to know the lactose intolerant and other related pathological conditions. Now we can take maltose. This is an example for alpha linkage. So what we have here is an alpha 1,4 glycosidic linkage. So it's very easy to name. You always look at the anomeric carbon. That is the preference here. And even this is a reducing sugar. And therefore we have a non-reducing end here, reducing end here. Now if we take fructose as Pyranose and Furanose rings. So the glucose and fructose, the sucrose, this is the disaccharides. We have fructose and D-glucose linked together. This is all alpha linkage because of the orientation here in the axial position, alpha 1,2 glycosidic